All right, welcome back, College Chem. We're going to talk today about the difference between endpoint and equivalence point in terms of our titration. So one thing to kind of give you a little bit of background on is just to make sure that you understand what pH means. Because we're going to be using pH meters, pH probes as we kind of do part of the lab. And for you to understand what a pH probe or measures, it really has to do with the hydrogen ion concentration. That's actually what pH is. So if you look closely here, and don't worry, we're not going to actually do the calculations. If you take AP Chem, you'll get a much more detail about the calculations. And you might have done a little bit of pH calculations in first year chemistry just briefly, but pH is the negative log of the hydrogen ion concentration, okay? So when we see something like something has a pH of 2, what does that really mean? Well, that means that the hydrogen ion concentration is 1.0 times 10 to the negative 2 molarity, okay? So that's actually pretty high in terms of hydrogen ion concentration. If you see a -1 here, that's 0.1 molar. If you see -2 here, it's 0.01 molar and so on. A pH of 9, notice, is a -9. That's a really, really small hydrogen ion concentration. So there's a connection here in terms of hydrogen ion concentration and pH. The pH, if it's greater than 7, so we have a really small concentration of hydrogen ion because the pH value is greater than 7. If it's greater than 7, we would typically say the solution is basic. It basically has more OH minus ions floating around in solution than it would have H plus ions. And that's why it is considered to be basic. If the pH is less than 7, the solution we would say is acidic. So if we have a high concentration of hydrogen ions, then we should have kind of a low pH, and therefore the solution is acidic. If the pH is actually at 7, we typically say, oh, that solution is neutral. So there's a good balance between the H plus ions and the OH minus ions, okay? So just remember that pH records or measures the hydrogen ion concentration. High pH means it's not acidic at all. It means it's very basic, lots of OHs. Low pH, that means it's acidic, has a lot of H pluses floating around. If it's neutral, we're at a pH of 7, so keep that in mind. Now, two things we were looking for in the lab. The difference between the equivalence point and the end point. The equivalence point, which is what we're talking about now, is when you do a titration and the moles or pieces of H plus ions present in the acid is exactly equal or equivalent in number to the number of moles of OH minus ions from the burette. So when we get this perfect balance between H's and OH's, that is what we call the equivalence point. Now, the end point, which we did in part 1 of the lab, that's when you put an, an indicator in the beaker or in the solution, and we go just barely past where they're exactly equal, and we get a little bit excess of something, and it makes the color change occur. So in the case of our lab, we put phenolphthalein in there, and we added sodium hydroxide until we went just barely past those being equal, and we get a little excess OH that causes that pink color. The goal really is always the equivalence point. When we actually have the exact number of H's and OH minuses balanced, but visibly for us to see it, that's really hard for us to do. That's why we typically use endpoints. So we're going to talk a little bit more about equivalence point here. Just to give you kind of an indication of what type of indicators we potentially would use. Maybe you've seen some of these before. I'm going to kind of highlight a few of them on this slide. Maybe you've heard of litmus before on the I would say about halfway over litmus right here. Sometimes we use what we call litmus paper. It's pink paper or blue paper. And notice here, there's a line about here that separates pink from blue. Basically what it means is this litmus paper, when it's in a low pH acidic solution, it will be pink in color. But if we put it in a basic solution, it'll be kind of bluish purple in color. And notice that color change occurs right at 7. So this is a really common indicator to use if we know that the equivalence point is going to be close to 7, litmus is a great thing to use. And that's a lot of times, first year chemistry, we use litmus paper just to kind of dip and test, is it an acid or is it a base, and based on the color of the litmus paper. Now, let me point your attention over here to, phenolphthalein, which is what we used in the lab. If you look closely there, the color change from clear to pink actually doesn't occur right at 7. It occurs about here, which looks like just barely above 8. That's okay. It's fairly close to 7. A lot of times we're just trying to get somewhere in the ballpark of where we need it to be. But some of these other indicators, let me show you the first one here, this methyl violet in the beginning. Notice then when it's really, really acidic, close to 0, it's kind of a yellowish color, and then it looks like it's a green and then a light blue. Usually we would use, if we wanted kind of the color change here, we would have to know that our equivalence point occurs between 1 and 2. And probably the question you're having is, well, why would it occur anywhere else besides 7? I thought acid and a base perfectly neutral would be at 7, but notice these indicators have color changes kind of at different pHs. The point of using an indicator is to try to figure out which indicator will change colors where you think the equivalence point should be. And so that's where we have to have some conversations. Equivalence point doesn't necessarily always occur at 7. Okay? If we have a strong acid and a strong base, we have the acid and the base and we put them together, we will actually get an equivalence point when it's neutral. If you look here on the graph, here's what's going on. Let's talk about this graph. We have a pH on the y-axis, and we have cubic centimeters, that's the same thing as milliliters, of sodium hydroxide added. So the way this is kind of set up is this tells you at the very beginning we didn't have any sodium hydroxide, so it looks like our acid is the unknown, and we are adding slowly a little bit of sodium hydroxide. We're kind of going this direction. And what we're doing is we're monitoring the pH as we go and as we continue to add base. So maybe at the very beginning here, the pH probe was reading, man, it was reading really low, really close to 0. We add a little bit of sodium hydroxide, maybe 10 milliliters, pH comes up a little bit. Then we add some more, we get to 20 milliliters of sodium hydroxide, the pH comes up a little bit. We get to 30, hey, that pH comes up a little bit. But notice when we get to 40, we actually start to see an increase in our pH. We see our pH coming up a little bit. Now, not a lot, but it does increase a little bit. And so what we're doing here is we're monitoring the pH as we continue to add sodium hydroxide. When we add, maybe let's say that, let's call this about 48. Notice the pH is up to 2. And then notice how steep the curve is. So it looks really like once we get to between 40 and 60, we're going to see some significant increases in our pH. So we would have to go really slow. We add like 1 drop at a time, and we continue to track the pH as we go. And as that happens, we see some significant jumps in the pH. But once we get past this spot, let's say we get to pH of 10, and then we continue to add, and we get up to here, maybe once the pH is at 12, we look down and we say, oh, we added somewhere around, oh, maybe 55 milliliters, and then we add a little bit more, we get to 60. And notice this starts to level off. And that's what's going to happen when we track our pH. Here's what we're looking for. We're looking for the steepest part of the pH curve. We get kind of this S curve, right? We're looking for where in this graph do we get the most significant or fastest change, the steepest part of the graph. We want to take the midpoint on that steepest graph, and if you look closely, it kind of occurs right in here. I'm going to put an X on it. That point right there on the graph, that is what we call the equivalence point. It is where the H's have perfectly equaled out the OHs, perfectly balanced out. in terms of the stoichiometry. So what we would do from that is we would say, okay, what's my volume? We'd read it. Hey, that looks right on 50.0 milliliters. And then we go over here and we say, what's my pH? Hey, that looks right at 7.0. So we could actually take a reading from this graph and say, hey, the equivalence point occurred at 50 milliliters. We would use those 50 milliliters of sodium hydroxide to move forward with the calculation just like we did before. We would also look at this pH and say, hey, that's perfectly neutral. That's at 7. Anytime we have a strong acid and a strong base, you can expect the equivalence point to occur at a pH of 7. Okay? Basically, what's going on is because it's a strong acid, all of the H's break off of the acid, because it's a strong base. All the OH minuses break off. And since they're all a bunch of H's and OH's floating around, they perfectly balance each other out at the same time that we get to the pH of 7. Okay. Now let's move on to the next slide. And I want you to look at this one. I want you to look at what things are different. We have some similarities, right? We're still dealing with pH along the y-axis. We're still adding our milliliters or cubic centimeters of sodium hydroxide. So we must start with the acid in the beaker, and we're slowly but surely adding the base, right? A couple things that you should notice that are different here. There's kind of this weird curve at the beginning that we didn't see before. But probably more importantly, here's what you need to notice. This equivalence point, which occurs right here, the steepest part of the graph, if we were to read the pH on that, that is not at 7. That is somewhere between 8 and 10. I'm going to call it 8.5. It doesn't actually occur at 7 here. So here's what you need to catch. The reason why the equivalence point, although the volume still looks about 50, right? What's different here is the combination is a weak acid and a strong base. Weak acid and a strong base. When you have a strong base, you have a lot of OH minus ions floating around. All of the pieces break up. But when you have a weak acid, I'm going to use HF as my weak acid, that doesn't dissociate. So most of the pieces are still intact as HF. When that occurs, that means when you actually equal exact numbers of HF is exactly equal to the OH minus ions, because really what we're talking about is balancing the H's with the OH's. When those two are equal to each other, we've got a lot of OH's still floating around in the beaker. And because of that, that drives up our pH to be greater than 7 for the equivalence point. So at this point here where they're exactly equal to each other, we have more OHs floating around. And this is because we're dealing with a strong base and a weak acid. That's something you're going to want to remember. The equivalence point occurs between a weak acid and a strong base greater than 7. Think of it like a tug of war. On the previous one, strong acid, strong base, tug of war against each other, nobody wins. It's a tie. It's neutral right at 7. In this case, strong base versus a weak acid, tug of war, who's going to win? The strong base. And what that does is that pulls the equivalence point above 7. It pulls it into the basic range. And that's something you're going to want to know. Okay. All right, moving on to the next slide. Let's look closely at this one. What do you notice about this that's different? We have some similarities. pH is still on the y-axis, right? But what's different is the graph is starting up here and it's ending down here. It's basically going the opposite direction. Well, how come? Look closely here. We're adding milliliters or cubic centimeters of HCl this time. So we start with a high pH because basic solution will have a high pH, and we are slowly but surely adding acid to the base and neutralizing it. Okay, we do see this little curve here at the beginning, but what I really want you to focus on here is the equivalence point. If we look for the steepest part of the graph, midpoint of the steepest point, there's our equivalence point. We could read the volume again. Hey, that looks like 50 milliliters again, but more importantly, read the pH. It looks about 5.0 on the pH scale. Why does this occur? How come the equivalence point is now in the acidic range below 7? If you think about what's going on, we have a strong acid, something like HCl, perfectly dissociates. You have a bunch of H pluses floating around in solution. A weak base, something like ammonium hydroxide, doesn't dissociate. Not very much at all. And so what occurs here is when these two quantities or amounts are stoichiometrically equal to each other, the H's perfectly balance the OH's, we have a bunch of H plus ions floating around in solution, and we don't have those OH minuses free to come and connect and make more water. And so because we have some excess H pluses floating around, it makes our pH on our equivalence point get pulled below 7. So again, going back to the analogy of tug of war between strong acid and weak base, who wins? Well, the strong acid does. It pulls that equivalence point to be below 7, in this case, about 5.0. Okay? All right, let me clear this and let's move on to the next slide. Summary, here's what you need to know. When we're dealing with the equivalence point, and the equivalence point is when our H pluses are equal to OH minuses in terms of just counting for stoichiometry purposes. If we put a strong acid and a strong base together, the equivalence point is equal to 7. Strong acid, weak base, strong acid wins. The equivalence point is going to be less than 7, which is acidic, right? If we have a weak acid and a strong base together, and the equivalence point in this case is going to be greater than 7. Why? Because there's more OH minus ions floating around in solution. All right.